In this video, we will give a detailed description of a specific polynomial function using the tools that we've developed so far. So consider the following function. F of x equals 2x cubed minus 2x squared minus 40x. The leading term of this polynomial is the term with the largest exponent, which in this case is 2x cubed. So the leading term is 2x cubed, and the reason this is important is because it dictates the end behavior of this polynomial function. The degree of the polynomial function is the power of the leading term, so in this case the degree is 3. So using the leading term, we can actually describe the end behavior, or how f of x varies as x increases or decreases without bound. As x increases without bound, f of x behaves like 2x cubed, and 2x cubed increases without bound as x increases without bound. So we would write, as x increases without bound, f of x also increases without bound. Now, as x decreases without bound, f of x still looks like 2x cubed, but as x decreases without bound, x cubed is negative in a really large number, and so 2 times that really large negative number is again a really large negative number. So we would say that f of x decreases without bound. As x decreases without bound, f of x also decreases without bound. In answering those questions, we really just had to look at this leading term. It tells us a lot about the end behavior of a polynomial function. Okay, so a vertical intercept for a polynomial function is really just the output value when the input value is 0. It's like a y value when x equals 0. So if we want to know the vertical intercepts, we can just evaluate the function at x equals 0, which gives us 2 times 0 cubed minus 2 times 0 squared minus 40 times 0. Since each one of those terms we're multiplying by 0, that ends up just being equal to 0. So in this case, our vertical intercept is 0. To find a horizontal intercept for a polynomial function, we need to find values of x, or input values, that produce an output value of 0. So what we're looking for is values of x such that f of x is equal to 0. Recall that the zero product property helps us out with this task a lot if we can write our function definition in factored form. So if we take this polynomial expression here, 2x cubed minus 2x squared minus 40x, and write it in factored form, it'll be a lot easier for us to identify horizontal intercepts. So if we rewrite this, we could write this, we'll factor out a 2x. Notice that each one of these terms has a 2x in it. So 2x times some polynomial expression. From 2x cubed, we took away 2x, which leaves us with x squared. And then minus 2x squared turns into a minus x, and minus 40x turns into minus 20. Okay, so x squared minus x minus 20, we can actually factor that expression. So we have 2x times x plus something times x plus something. So what two numbers multiply to give us negative 20 and add to give us negative 1? So if you think about that a little bit, we should have x minus 5 and x plus 4. So we can rewrite our function definition as 2x times x minus 5 times x plus 4. If we want to know values of x that make that entire product equal to 0, then x equals 0 will do that. X equals 5 will make that factor equal to 0, and x equals negative 4 will make that third factor equal to 0. And therefore, x equals 0, 5, and negative 4 all give us an output of 0, and therefore, our horizontal intercepts are going to be 0, 5, and negative 4. If you pull open a graphing calculator and plug in our original function definition, you should be able to check and verify that all of these things are true. You can verify the end behavior, you could verify the vertical intercept, and you should see that each one of these values of x produces an output value of 0. So at those values of x, the function graph will touch the horizontal axis.